In this video, we'll be discussing section 7.9 from chapter 7 of P4, and we'll be discussing the equation of a straight line in 3 dimensions. Okay, in 3 dimensions using vectors. Alright, so let's consider that we have a 3D space. Okay, I'll not draw the x, y, and the z axis for the time being. Okay, so let's consider that we have a 3D space with three of our coordinate axes x, y, and z, and you have a straight line. Okay, and you have a straight line. Okay, now on this straight line, we need to find the equation of the straight line. Okay, in the vector form, and we have the origin O. Okay, somewhere in the vastness of this 3D space. Okay, and we have this point which is A. Okay, so if this point is A, in that case we have the position vector for A, which is going to be simply position vector for A. Okay, is simply going to be a small letter A over here. Okay, and we know that A lies on this line, therefore position vector A gives you the coordinates. Okay, position vector A is going to end on this line. Okay, now let's say that you have a vector B. We have a vector B that is parallel to this line. Okay, so you have a vector B that is parallel to this line. In that case, now we can find the position vector of any point on this line. Okay, so let's say if you have this particular point on this line, we have this particular point on this line, or this point on this line, or even in the opposite direction. Okay, we can have any point on this line, and you can find the position vector of that point. Okay, so let's say that this particular in each of this case, okay, whatever the vector over here is, okay, this vector is going to be, okay, this particular vector that I'm drawing, okay, this portion of this vector are all going to be parallel to B. Okay, they're all going to be parallel to B. Okay, and so since they're all parallel to B, they're simply a scalar multiple of B. Okay, so let's assume that the scalar multiple of B is going to be lambda B. Okay, and the scalar multiple of B is lambda B. In the first case, maybe this is 1B. In the second case, this is 2B. In the third case, we have 3B. In this case, we have minus B. In this case, we have minus 2B. And the last case, we have minus 3B. Okay, so we have A, which is the position vector of one of the points, and the other points from A, if we move on, we have B, we have 2B, we have 3B. Now the overall position vector needs to start from O and not A, and the overall position vector is going to be, okay, so if the point is P, P1, P2, P3, P4, P5, P6, in general, the position vector at the point P is going to have position vector OP equals OA plus AP. Okay, and the point P is going to have position vector OP equals OA plus AP. OA is always A. Okay, OA has position vector A, and AP, okay, depending upon where P is, okay, P could be anywhere along the line, AP is going to be a multiple of the vector B. Okay, so it is equal to plus lambda B, where lambda can change. Okay, so A is the position vector of a particular point on the line, and B is a vector that is parallel to the direction of the line. Okay, this is therefore, okay, OP, we can rewrite this as R, okay, where R is the position vector of any point on the line. Okay, so this is your general equation for a line in the vector form. Okay, R is the position vector of any point on the line. Okay, this is equal to A, which is the position vector of a particular specific point on the line that you know. Okay, this is something we know, and B is the vector that is parallel to the direction of the line. Okay, so B does have a special name. B is called the direction vector of the line. B is called the direction vector of the line. So if you know the direction vector of the line and you know a particular point of the line, in that case you can find the overall vector equation as R is equal to A plus lambda times B. Okay, so lambda times B, okay, that gives the lambda gives you different points along the line. Okay, now in this case we were given the direction vector B. Okay, but it is possible that the direction vector is not given and you need to find the direction vector. Okay, so let's say that we do have a line, okay, and you do have a point O, okay, and over here let's say that we have a point M, okay, which has position vector M, and we have another point N which is position vector N, and that's it. That's all we are given to find the equation of this line. Okay, so now in this previous case we needed a point on the line. Here we have 2 points on the line. We can use any one of them, it does not make a difference. Okay, we need a point on the line. Here you have 2 options, but we do not need a direction vector. Okay, we do need a direction vector. In this case the direction vector was given to us as B. In this case the direction vector is not given to us, but since we have 2 points on the line, we can actually easily find the direction vector. The direction vector is simply Mn, okay, because Mn does follow the line. Okay, Mn is parallel to the line, is lying along the line. Okay, therefore Mn is definitely your direction vector. Okay, therefore the direction vector Mn, okay, is going to be simply Mo plus On, okay, which is minus Om plus On, which is simply minus M plus N. So you get your direction vector, and then the rest is going to be simply using this formula. Okay, therefore R is equal to, we can use M or N, so we can R is equal to M plus lambda times minus M plus N. Okay, if you want to use N, in that case R is equal to N plus mu times minus M plus N. Okay, and notice that if you're using M, it does not matter whether you use lambda or mu or interchange them. The reason that I've used 2 different parameters is that because here you have used M, this is one version of the line. Here you have first used N, even though they're going to give the same line, okay, but the parameters are going to be parameters are going to be different. Okay, for the same point, for the exact same point, the parameters are going to be different. Okay, so let's not worry about that for the time being. The only thing that matters to us is that you can use any of the points. It does not matter whether you want to use M or N, is up to you. Okay, the direction vector was found by using Mn, okay, because Mn does definitely follow the line, is lying along the line. Okay, and thus you can find out the direction vector using the expression minus M plus N. Now let's consider an example. Okay, example 32 on page 127. In this particular example, they have given us 4, 5, minus 1. Okay, is the first point that they have. Okay, and the other point that they have is 6, 3, 2. And they're asking us to find a vector equation of this line. Okay, a vector equation of this line where this is A has coordinates this and B has coordinates this. Okay, so since A has coordinates this, B has coordinates this, we can find out the position vectors of A and B. So position vector of A is equal to 4, 5, minus 1. Position vector of B is 6, 3, 2. Okay, now we do need the direction vector. Okay, we do have 2 points on the line. Okay, we can use any one of this, it does not make a difference, but we do need the direction vector for this line, and the direction vector, okay, can be given, by AB or BA. Does not make a difference again which one you use, because both AB and BA are going to be parallel to the line. So if you use AB is going to be equal to minus A plus B, which equals 2 minus 2, 3. Okay, so we have 2 minus 2 plus 3. Once you get this, the rest is going to be using the formula. Okay, so R is therefore equal to, you can use A or B, does not make a difference. Let's use A for the time being. We have 4, 5, minus 1 plus, you can use lambda, mu, does not make a difference what parameter you use. We can use T as well. Okay, and 2 minus 2, 3. Alright, so R is equal to 4, 5, minus 1 plus T into 2 minus 2, 3, and that you can simplify this expression if you want to. Okay, and this becomes 4 plus 2t, 5 minus 2t, minus 1 plus 3t. Okay, on the other hand, if you want to use the other point, if you want to use B as your starting point, in that case R is going to be equal to 632 plus S. Okay, you're using a different parameter because you used a different starting point. Okay, because the same value of the parameter is not going to give you this same answer for both of these lines. Okay, so s into what is it, 2 minus 2, 3. Okay, and that is going to give you 6 plus 2s, 6 plus 2s, 3 minus 2s, 2 plus 3s. Okay, so both of these are acceptable forms of the line. Okay, it does not matter whether you use A or B. Okay, now let's consider example. Let's consider, a very similar question to what you have in example 33. Okay, in example 33 they have a question where you're asked to find the coordinates given that a point lies on the line. We'll do a similar question, and this question is going to be exercise 7I, question number 4c. Exercise 7I, question number 4c. Okay, and in this question they are saying that, okay, we have a point 1 comma p comma q, 1 comma p comma q is lying on the line L, and L has the equation for 4c. Okay, question number 4c, L has the equation 16 minus 9 minus 10 plus lambda, okay, times 3, 2, 1. Okay, 16 minus 9 minus 10 plus 3, 2, 1, and the point 1 comma p comma q lies on this line, and I need to find out what p and q are. In other words, complete the coordinates. Okay, so since 16 minus 9 minus 10 plus lambda 3, 2, 1, okay, is the equation of the line, okay, and 1 comma p comma q does lie on this line, therefore for some value of lambda definitely we'll have 1 pq equal to this equation. For some value of lambda, you need to find the value of lambda as well. Okay, so let's combine the equation. This equation is going to become 16 plus 3 lambda, 16 plus 3 lambda minus 9 plus 2 lambda minus 10 plus lambda. Okay, this is equal to 1 pq. Okay, again 16 plus 3 lambda minus 9 plus 2 lambda minus 10 plus lambda equals 1 pq. Okay, and all the three components are going to be equal to each other. Okay, the x components on both sides are going to be equal to each other, the y components are going to be equal to each other, the z components are going to be equal to each other. Therefore 16 plus 3 lambda equals 1, 16 plus 3 lambda equals 1. Solve the equation, you get lambda is equal to minus 5. Okay, now once you get lambda equals minus 5, okay, substitute this into the second remaining two equations to find the other components. Minus 9 plus 2 lambda, minus 9 plus 2 lambda equals p. Substitute p equals minus 5, you get p is equal to minus 19. And then minus 10 plus lambda equals q. Substitute q equals lambda equals minus 5, and you get q is equal to minus 5, and therefore the overall coordinates are going to be 1 comma minus 19 comma minus 5. Okay, again, okay, you have three equations, so solve all the three equations. Okay, the first equation gives you the value of lambda, the remaining two equations are going to give the values for the remaining two coordinates. Alright, now let's consider example 34. Okay, in example 34 they have given that the vector equation in question has got equation r equals 2i plus 5j minus 3k, r equals 2i plus 5j minus 3k plus lambda times 6i minus 2j plus 4k. Okay, and the question is saying that show that another version of this equation is r equals 8i plus 3j plus k, okay, plus mu times minus not minus 3i minus j plus 2k. Okay, so this is the original equation of the line, so this is our starting point. Okay, because this is what the question says is the equation of the line. Okay, as a fact. Now the question is to prove that this is also a correct equation for this line. Now to prove that this equation is also correct, is also acceptable, we need to prove two things. First thing is this, and the second thing is this. Okay, we do need to prove two things. Okay, so here we have this equation where this is one of the points on the line and this is the direction vector of the line. Over here we have this as the point on the line, the fixed point on the line, and this as the direction vector of the line. So we need to prove two things, that first this is correct, the second thing is this is correct. Now what is the first thing over here? The first thing is 8i plus 3j plus k. We need to prove that this point, okay, this point, what is this point represent? This is not the direction vector. The direction vector is this one. This point represents a fixed point on the line, okay. We know, in other words, 8i plus 3j plus k is the position vector of one of the points on the line, okay. So since this point, okay, 8 comma 3 comma 1 lies on the line, it definitely should be equal to some this equation for some value of lambda, okay. So in other words, for some value of lambda, which you are not sure what it is, okay, for some lambda, okay, 2i plus 5j plus 3 2i plus 5j minus 3k, 2i plus 5j minus 3k plus lambda times 6i minus 2j plus 4k is equal to 8i plus 3j plus k, okay. So for some value of lambda, we're not sure what lambda it is, okay. This equation should be true because this point should lie in the line, okay. This point should lie in this line. If this point does not lie in this line, you cannot use that point to write the equation of the same line again, okay. So definitely this point should lie in this line, and therefore for some value of lambda, this equation should be true. Now just as in the previous question that we solved, okay, let's write this down in a column vector form, because writing this in column vector form is going to make our working easier, okay. So you have 2 plus 6 lambda, 2 plus 6 lambda, 5 minus 3 minus 2 lambda, and then plus 4 lambda. This is equal to 8, 3, 1, okay. So 2 plus 6 lambda, 5 minus 2 lambda minus 3 plus 4 lambda on the left hand side is equal to 8, 3, 1 on the right hand side. Now let's solve the first equation, okay. 2 plus 6 lambda equals 8, okay. Lambda is equal to 1, okay. Now lambda is equal to 1. Now we need to see whether lambda is equal to 1 is satisfies the other two equations, okay. So in the second equation, you have 5 minus 2 lambda equals 5 minus 2, which equals 3. So it does match. 5 minus 2 lambda is equal to 3 if lambda is equal to 1, okay. What about this one? We have minus 3 plus 4 lambda, which equals minus 3 plus 4, which is equal to 1. So this is equal to 1 when lambda is equal to 1. In other words, lambda equals 1 satisfies all three equations, okay. So since lambda equals 1 satisfies all three equations, this point does lie on the line, and therefore the first part is proven, okay. So this point lies on the line. We found it out by finding out a value of lambda that satisfies this particular equation, okay. Here lambda equals 1 satisfies the equation. When lambda equals 1, r on this equation is equal to this, okay. This particular point, 8i plus 3j plus k. So therefore this point lies on the line, and therefore the first part is proven. Now the second part is 3i minus j plus 2k. 3i minus j plus 2k, we need to prove that this is also acceptable as a direction vector. Notice that our original direction vector is 6i minus 2j plus 4k, okay. So our direction vector is 6i minus 2j plus 4k, and this can be written as, notice that these two are actually parallel to each other, so since these two are parallel to each other, okay, it means that they are more or less following the same direction. They're like the only difference is that they are not of the same length, okay. The two vectors are not of the same length, but they are parallel to each other, and therefore they are going to be it is possible to express them as scalar multiples of each other. So 6i minus 2j plus 4k can be written as 2 times 3i minus j plus 2k, okay. So since 6i plus minus 2j plus 4k, that is the first direction vector, is equal to 2 times 3i minus j plus 2k, these two vectors are parallel to each other, okay. So therefore this vector, let's call it for the time being b1, okay, and this vector, let's call it b2, okay. So b1 and b2 are parallel to each other. So b1 and b2 are parallel to each other. So since they are parallel to each other, okay, it does not matter whether you use b1 as the direction vector or b2 as the direction vector, as long as you have a vector that points along the direction, okay. It does not matter whether it's b1 or b2, okay. This vector is also acceptable as the direction vector, and therefore the second part is proven, and thus this equation is acceptable, as as a as an equation for the line. Okay, the only difference, notice the only difference is that we are having lambda here and mu over here. Okay, now if they ask us, we can write the equation for the same line in different manners. Okay, let's say that if lambda was minus 10. Okay, so if lambda was minus 10, next from this equation, what is r then? R is equal to 2 plus 6 times lambda, that is equal to minus 62. So 2 plus 6 times lambda is minus no, it's not minus 62, it's minus 58, sorry, minus 58i. Minus 10 for the second one is going to give you 25 plus 25j. Minus 40 minus 3 is going to be minus 43k. Alright, okay, so this is also acceptable as the starting point, and then we write plus t. I'm using a different parameter from the first two, and over here let's say that we have this vector and we multiply this by minus 10 as well, or let's say minus 5, just minus 5. Okay, so if you multiply by minus 5, in that case you get minus 59 plus 5j minus 10k. Notice that since this vector and this vector scalar multiples of each other, I multiply by minus 5 to get this vector. This is also acceptable as a direction vector. Okay, as long as it points in the same direction, it does not make a difference. Okay, therefore this equation is also representing the same line. This equation, all the three equations are referring to the same line. Okay, now let's consider example 34. Let's consider example 34. In example 34, they have no, this was example 34. Let's consider the next example. So the next example is example 35, and in this question, they have a line with vector equation r is equal to minus 214 plus lambda times 1 minus 2 1. Okay, and the point P has, and this is the equation of the line. Now there is a separate point P which has position vector 2 1 3. Okay, so OP is equal to 2 1 3. Okay, and the first part of the question is to prove that P does not lie on R. Okay, so the first, in the previous questions we were asked, in the very the question over here, we were asked to prove that this we were asked to find out P and Q, and this point was lying on the line. In this question we are asked to prove that this point does not lie on the line. Okay, so let's rewrite this equation as a single column vector. You have minus 2 plus lambda, 1 minus 2 lambda, and 4 plus lambda. Okay, and if P lies on the line, in that case 2 1 3 should be equal to this thing. Okay, so if P lies on the line, okay, 2 1 3 should be equal to this thing. Okay, what do you get when you solve the first equation? Okay, from the first equation we get minus 2 plus lambda equals 2, lambda is equal to 4. Does 4 satisfy the other two equations? In the second equation you get 1 minus 2 lambda is equal to 1 minus 8, which is equal to minus 7, and in the second one, in the third, the very last equation, you get 4 plus lambda is equal to 4 plus 4, which equals 8, minus 7 is not equal to 1, and minus 8 is not equal to 3. Okay, so it does, the two lambda equals 4 does not satisfy the entire equation, and thus this particular vector, this particular position vector, this particular vector does not lie on this particular vector equation. Okay, or, in other words, point P having coordinates 2 1 3, point P having coordinates 2 1 3 does not lie on this particular line that is represented by this particular vector equation. Now in the second part of the question, they're saying that we have a circle and that has got center P. So P is the center of this circle, and it is intersecting L at points A and B. Okay, so P. Okay, so let's draw a very rough sketch. Okay, so we have a line. We have a circle that is going to intersect it at 2 points. okay, and P is not on the circle, P is not on the line, and P is the center of the circle though, and P is not on the line, and you know P is not on the line because of this thing. Okay, you already solved it out. Okay, P is not on the line. If P was on the line, let's assume that if P was on the line, in that case we'd have had a circle like this. Okay, where P is on the line. Okay, but in this case we already proved in part A that P does not lie on the line, therefore P cannot be on the line. It is just the center of the circle, and that's it. Okay, so P is lying on a P is center of the circle, and the circle is intersecting the line at 2 points. We have points A and B, and A, we have points A and B. Does not matter where A and B lie. Okay, I mean it does not need to be exact. Okay, because we are drawing a 3D sketch on a 2D plane, so it's just a rough sketch. Okay, but we have A and B as 2 points of intersection between the line and the circle, and A has position vector 0, minus 3, 6, or in other words it has got coordinates 0, minus 3, 6. The question is to find the position vector of B. Okay, so how do we solve this again? Okay, so we have A 0, minus 3, 6, and here we have the point P, we have point B over here. Okay, we know the equation of this line AB. Okay, so we know the equation of line AB, equation of the line on which A and B are lying. Okay, so this is your line L. Okay, this is your line L, this is your circle. Okay, and we need to find out the position vector of B. So now for B, let's assume we have the equation of the line over here. Okay, so for B, let's assume that lambda is equal to some constant. Okay, so for B, let's let lambda equal, for at B, let lambda equal h. Okay, I mean because lambda is changing, okay, along the line. Okay, lambda could be anything along the line. For every point along the line, lambda is going to be different. For B, let's assume that lambda is equal to h. In that case, what is the position vector of B? Position vector of B OB is equal to, the position vector of B OB is equal to minus 2 plus lambda, minus 2 plus h, sorry, minus 2 plus h, 1 minus 2h, 4 plus h. Okay, this is only for B. Okay, the position vector of B has got lambda is equal to h, therefore minus 2 plus h, 1 minus 2h, 4 plus h. Now, okay, now let's find, we have the, so we now have the vector for the position vector for B. We have the position vector for A. Okay, OA is equal to 0, minus 3, 6. Okay, OA is equal to 0, minus 3, 6. Okay, usually column vectors are going to help you when you do 3D vectors and solving 3D vectors. Trying to use the IJK vector notation can sometimes make it confusing, because there is a high chance of messing up the I and the J components over here. It's easier to visualize who's I, who's J, and who's the K component. Okay, so OA is equal to 0, minus 3, 6. This was given in the question, and in the question it was also given that OP is equal to 2, 1, 3. Okay, now notice that since this is a circle, PA and PB should be of the same length. Okay, so that is the fact that you're going to use in this question. Okay, PA and PB should both have the same length. Okay, so let's first find the length PA then. Okay, let's first find the length PA. Okay, so PA length is the same as the magnitude of vector PA. Okay, PA is the same as the magnitude of vector PA, and that is going to be PA is equal to PO plus OA, excuse me, PO plus OA, which is equal to minus OP plus OA. Okay, and that is equal to minus OP plus OA, so we have OA minus OP, okay, and that is minus 2, minus 4 and 3. Okay, and you're going to take the magnitude. That's why you have the straight lines over here. Okay, the straight lines just continue throughout, but now you're going to calculate the magnitude. This is going to be root of 4 plus 16 plus 9, and that is equal to root of 29. Okay, so since PA is equal to root of 29, PB is also equal to root of 29, because they're both the radius of the circle. Okay, so PB is equal to root of 29. Let's calculate what PB is. Okay, first let's calculate the position vector, not position vector, the vector PB. Okay, let's calculate the vector PB, and PB is equal to PO plus OB. PO is equal to minus OP plus OB. We have OB here, we have OP here. Okay, therefore OB minus OP is going to be equal to minus 2 plus H minus 2, 1 minus 2H minus 1, and 4 plus H minus 3. Alright, so that's your vector. So let's simplify the expression. We have minus 4 plus H minus 2H 1 plus H. Okay, minus 4 plus H minus 2H 1 plus H. Okay, so that's your expression for PB. Now the modulus, the magnitude of this vector is going to be, PB modulus. Okay, and that is going to be equal to minus 4 plus H the whole square, minus 4 plus H the whole square, plus minus 2H the whole square, plus 1 plus H the whole square, and then the whole root. Okay, and that is equal to root of 29. Okay, we got this from the while solving for PA, we found that P was 29. Therefore PB modulus is also going to be equal to root of 29. Okay, now the rest is going to be simply solving for H. Okay, so let's solve for H. We get, the first thing we're going to do is square both sides of the equation, remove the square root. Okay, now expand this side of the equation. You get H minus 4 the whole square is equal to H square minus 8H plus 16 plus 4H square plus H square plus 2H plus 1, and that is equal to 29. Okay, now let's simplify the equation. Let's take 29 to that side as well. H square plus 4H square plus H square is equal to 6H square, minus 8H plus 2H is equal to minus 6H, and then plus 16 plus 1, 17, minus 29 is equal to minus 12, is equal to 0. Okay, now solve this equation. You get H square minus H minus 2 is equal to 0, H minus 2, H plus 1 is equal to 0, H is equal to minus 1 or 2. Okay, H is equal to minus 1 or 2. Now our question is to find the position vector of B. Let's see what happens when you substitute 2 into this equation. When you substitute 2 into this equation, we get minus 2 plus 2 is 0, 1 minus 4 is equal to minus 3, and 4 plus 2 is equal to 6. Okay, but notice that 0 minus 3, 6 is actually the position vector of A. Okay, so 2 is actually for A and not for B. Okay, so when you substitute 2, 0 minus 3, 6 you get, and that is the position vector of A. We need to find the position vector of the other one. Okay, we already have A with us. We need to find the position vector of the other one, and for that you need to substitute minus 1. Okay, so substitute minus 1 into this equation. We get OB, the position vector of B is given by minus 2 minus 1 is equal to minus 3, 1 plus 2 gives you 3, and finally 4 minus 1 is equal to 3. Minus 1, minus 2 minus 1 is equal to minus 3, 1 plus 2 is equal to 3, and 4 minus 1 plus 2 is equal to 3. Yeah, alright, so that's your final answer, okay, to this question. Now, before you move on though, it's often common when solving when questions for this come P4 vectors. Okay, now questions for P4 vectors often ask about parallel lines. Okay, so let's say that you have a vector equation let's say that you have a vector equation R is equal to some vector plus lambda times some vector, okay, and you're given, okay, so let's say that this is vector A, this is vector B, okay, and you're given another point, okay, let's say you're given a point C which is vector, which has coordinate something, and from that coordinates of C you can find out what the position vector C is, okay. And the question is asking that we need a line that passes through C and is parallel to this line, okay, this entire line over here. So we have a parallel line that passes through C. So whenever you have a parallel line in your question, parallel lines will have the same direction vector, okay, parallel lines have same direction vector. Okay, so parallel lines have the same direction vector means that you have C is a fixed point in the line that we are not going to do anything about, okay. The question has given us that, but if it says that you have parallel lines, in that case you're going to have the same direction vector. In other words, the direction vector for this line is going to be the same as the direction vector of this line, and that is going to be B, okay. So let's consider a question for this one. We have question number 9 on page 130, okay. Question number 9 on page 130 from exercise 7i, I guess. Yeah, 7i. Exercise 7i. Question number 9, page 130. And the question says that you have a line L1, which is equation. So line L1 has equation R is equal to 8i minus 5j plus 4k. 8i minus 5j plus 4k plus lambda times 3i plus j minus 6k. Lambda times 3i plus j minus 6k. Okay, again 8i minus 5j plus 4k plus lambda 3i plus j minus 6k, and the question says that A is the point on L1 such that lambda equals minus 2. So at A, lambda equals minus 2, okay, and with the line L2, okay, the line L2 has equation, it passes through A, okay, so the line L2 is passing through A and is parallel to the line, okay, the line L2 is passing through A, passes through A and is parallel to the line given by the equation R is equal to 10i plus j, 10i plus 3j minus 9k, 10i plus 3j minus 9k plus lambda times 2i minus 4j plus k. Okay, and they're asking you to find the equation for L2. Okay, so again we have L2, we need to find the equation for L2. So when we need to find the equation of L2, we need to again the general equation for the general equation for a vector equation of a line. The general vector equation for a line in 2 dimensions or in 3 dimensions is going to require you a specific point of the line, okay, and also the direction vector. Okay, so what does this question say about the specific point? A specific point is A, okay, L2 passes through A, so we need to find this position vector of point A, okay, and A can be found using the help of our first line, okay, because it says that at A lambda is equal to minus 2 for the first line. So let's substitute, use L1, use the first line, okay, and if lambda equals minus 2, in that case R is going to be equal to 8 plus minus 2 times 3 minus 5 plus minus 2 times 1 and 4 minus, excuse me, 4 minus 2 times 6, okay, substitute minus 2 into this equation and you get 8 minus 6 is equal to 2. 8 minus 6 is equal to 2 minus 5 minus 2 is equal to minus 7, and 4 plus 12 is equal to 16. Yeah, so we got a fixed point on the line. Okay, this is the this is OA. Okay, this is OA. Okay, and therefore we have our fixed vector, our fixed vector on the line, and we need to now get the direction vector. Now the direction vector is found by this particular part. Okay, it says that L2 is parallel to this particular line. So since L2 is parallel to this particular line, it means that both of them have the same direction vectors. In other words, our direction vector is simply this thing or a scalar multiple of this thing. It does not make a difference. Okay, so we have a direction vector 2i minus 4j plus k, 2i minus 4j plus k, or it could be 4i minus 8j plus 2k, or it could be 20i minus 40j plus 10k. Okay, it does not matter. All these are acceptable vectors. Okay, as long as it is the same direction vector. All these three are actually in the same direction. They are all parallel to each other. Okay, so since L2 is parallel to this line, okay, the direction vector is the same as the direction vector of this line. So 2i minus 4j plus k, let's use this one, the very first one, and thus L2 will have the equation. For L2, our equation is going to be R is equal to, okay, make sure your equation starts with R, not L2. L2 is not the way you start an equation. L2 is just the name of the line. Okay, this is just the name of the line. Okay, so R is equal to 2 minus 7, 16, plus 2 minus 7, 16 plus, you could use lambda, or you could use mu, or you could use t, does not make a difference. I'm going to use s. There's no reason why I'm using s. Okay, 2 minus 4, 1. Okay, so 2 minus 7, 16 plus s into 2 minus 4, 1, where 2 minus 4, 1 is the same as the direction vector of the other line. Okay, so you can write it in this way, or you could write this in the ijk vector notation. So you could use 2i minus 7j plus 16k plus s times 2i minus 4j plus k, or you could combine this up together. Okay, so you could write this as 2 plus 2s minus 7 minus 4s 16 plus s. Okay, so 2 plus 2s minus 7 minus 4s 16 plus s, and that's your final answer. Okay, any of these answers are acceptable as long as the question does not specify specific form. Okay, if the question does specify specific form, like use the ijk notation or use the column vector notation, in that case do follow what the question asks. Okay, now just deviating on the topic that you're discussing, we can actually find out the Cartesian equation for this, okay, line. Okay, so as of now, the only thing we have discussed is finding the vector equation. Okay, and finding the Cartesian equation is definitely not a part of P4. Okay, it is part of pure mathematics, further pure mathematics, if we do study further pure mathematics. But if you do want to find a Cartesian equation, notice that we have three components. Okay, the first component over here is the x component, the second component is the y component, the third component is the z component. Therefore, you can write this as x is equal to 2 plus 2s, y is equal to minus 7 minus 4s, z is equal to 16 plus s. Okay, are these the Cartesian equations? They are not. Why? Because even though we have x, y and z, we still have s. Okay, so since we have a helping variable s in our equations, these are actually the parametric equations. These are the parametric equations for our line. Okay, again, repeating what I said, the first component is the x component, the second component is the y component, and the third component is the z component. Okay, but these are still not the Cartesian equations because we do have an extra variable s, okay, a helping variable s, okay, and thus these are going to be the parametric equations. Okay, parametric equations were discussed back in chapter 3 of P4. Okay, so these are actually the parametric equations where you have a helping variable. Now if you want to convert this into the Cartesian equations, in that case you need to eliminate s. Okay, so let's find out expressions for s. Okay, so from the first expression we get, if we rearrange this, you get x minus 2 the whole by 2 is equal to s. Okay, we took 2 to the other side and then divided the entire thing by 2. From the second one we get s is equal to y plus 7 divided by minus 4. Okay, again I took plus minus 7 to the other side and then divided the entire thing by minus 4. And from the third equation we get s is equal to z minus 16 divided by 1. Okay, I took minus 16 to the other side and then divided the entire thing by 1. It does not make a difference actually. Okay, you could simply write it as z minus 16 and it would still not make a difference. Okay, so we have s equals this, s equals this, s equals this. Notice that all of them are starting with s. So s equals this, s equals this, and s equals this means this, and this are all equal to each other. And thus I can write the entire thing as x minus 2 by 2 is equal to y plus 7 by minus 4, which is equal to z minus 16 divided by 1. And that, okay, is the Cartesian equation of the line. Okay, notice okay that in this case you had s, that's why this were the parametric equations. Okay, you're using a helping variable s to help you find out what x, y, and z are. In this case you don't have any s, we have just x, we have y, we have z. Okay, we have 3 components, okay, x, y, and z, and therefore this is the overall Cartesian equation of the line. Okay, again to repeat, we have x, y, and z, so we have 3 components on 3 sides of the equation, that is the Cartesian equation of the line. But we do not need to worry about this because finding the Cartesian equation of the parametric equations are not part of P4. As long as we can get the vector equation, we are good.